Okay, so in the last video, we saw that in order to solve a non-homogeneous linear differential equation, you you need to know what's called the complementary solution. That's the general solution to the associated homogeneous equation. And we've talked about how to do that in the past, at least in the constant coefficient case. That's where we know the complete answer. And then, we need to find any what's called particular solution. And once we find that particular solution, we just mash that, we just add that to get to the complementary solution. And I visualize that as taking this n-dimensional complementary solution and just translating it in space by y sub p. And that new space, that translated space, that's our general solution to the non-homogeneous equation. Okay, still n-dimensional, but yeah. All right. So how do we find y sub p? Because we've already talked about how to find y sub c. We know how to solve it, homogeneous equations, at least in many cases. So how do we find the particular solution? Well, this is where we're going to use something called the method of undetermined coefficients, which is just another way of saying we make a real good, educated guess. Okay? So let's talk about this. The method of undetermined coefficients. And remember, y sub p is just one solution, just any solution. Okay? So we can use whatever means we have necessary. By any means necessary, we can try to find that solution. And as long as it works, then it works, right? So, yeah, we don't need to worry about how big is the solution space because we know by the existence and uniqueness theorem already that we just need one solution. And we're going to translate the complementary solution by it. Okay? So this is, we're given L of y equals f of x, okay? And the question is, how do we find a single solution, y sub p? And what the method of undetermined coefficients suggests is that we make a really good guess for y sub p based upon f of x. So the method of undetermined coefficients suggests making a guess based on the structure of f of x. So here is a very concrete example. And then we can talk more generally. Let me do this in blue. So let's say that we have the following differential equation. Y double prime plus 5y prime plus 6 equals, let's say, 2x plus 1. Then what's playing the role of f of x here is this 2x plus 1 here. And the thing that I want you to feel about this f of x is that it's a degree 1 polynomial. So you might guess that because f of x is a degree 1 polynomial, that y, our solution to this differential equation, could also be a degree 1 polynomial. You make the following guess. Because f of x is a degree 1 polynomial, maybe y is a degree 1 polynomial. Or maybe I'll say it a little differently. Maybe a solution is a degree 1 polynomial. And I'm thinking here maybe it's y equals ax plus b for some a and b. Maybe. It's just a guess. But if the guess works, then we win. So it might be worth just trying. What's y prime? Well, this is not hard. Y prime is a. And what's y double prime? Y double prime is 0. So now we can plunge all of that data into the left-hand side of our differential equation, okay? We're going to take all this data right here, and we're going to plunge it into here, into our differential equation. Now we calculate. Maybe I'll do this in purple. So y double prime is 0. Y prime is a, so we get 5a. And then we have, oh, I messed up. This should be 5 plus 6y. I apologize. That was an oversight on my part, right? That should be 6y. Otherwise, I should move the 6 over to the other side. Oh, I should have pretended that I was always thinking that. But no, I actually just made a mistake. What's y again? Y is ax plus b. So I have 6 ax plus times ax plus b. This is equal to 2x plus 1. Okay, now what I can do is expand this out, collect like terms. I get that 6ax, you agree, plus 5a plus 6b. And I'm going to put this in parentheses like this for reasons, is equal to 2x plus 1. Now, these polynomials are equal as functions, okay? They're equal as functions of x. And you can check that the only way that two polynomials can be equal to one another is if their coefficients are equal. We've used this before. Surely you've used that before in your life. By the way, what's happening under the surface there is that functions like 1, x, x squared, x cubed, x to the fourth, etc., those power functions are linearly independent functions. This is the reason why comparing coefficients like this is a legit move to make. But I'll not worry too much about that, just make that comment. In any case, what this allows us to do is deduce from this by comparing coefficients. Well, maybe I'll say this. We can compare this 6a here with this 2. So we know that 6a is equal to 2. And that 5a plus 6b is equal to 1. The constant terms are equal. Now, crucially, what this is a system of equations in two variables, namely a and b. So we can, from here, solve. It's really easy to solve this one. In general, it might take a little bit more work. We can solve this one so easily because we see from the first equation, for example, that a is equal to 1/3. And then once we know a is 1/3, we can plug that into the second equation. We can shove this fact into the second equation to learn that 5/3, or 5 times 1/3, which is 5/3, plus 6b is equal to 1. And this is now child's play, isn't it? Oh gosh, I hope so. I think this implies, and is implied by 6b equals negative 2/3. Man, it would be embarrassing to get this, mess this up. I don't know. And then we divide both sides by 6. And I think we get negative 2/9. What? No, we get negative 1/9, don't we? I knew something felt wrong. there was something wrong in the force. I wish I didn't say that out loud just now. Okay, so anyway, what this tells me is that a particular solution is y sub p equals 1/3 x plus, no, excuse me, b is negative, so I'll write minus 1/9 minus 1/9. Right, I'm looking here. This is my purported solution, ax plus b, and I've uncovered the values of a and b which make this happen. Y sub p is 1/3 x minus 1/9. Okay? So then what is the general solution to the differential equation? Well, to find the general solution to this differential equation, we need to go on to find y sub c. We need to find the solution to the associated homogeneous equation. So you can check that y sub c, the complementary solution, is c1 e to the negative 2x plus c2 times e to the negative 3x. Do you believe? In which case, I'm saying that the general solution to our non-homogeneous equation is y equals y sub p plus y sub c, which is 1/3 x minus 1/9, that's y sub p, plus c1 e to the negative 2x plus c2 e to the negative 3x. That's the full set of solutions to this differential equation here. Anything, for any value choices of c1 and c2, you will obtain a solution to this differential equation. Okay? This is the method of undetermined coefficients in the particular situation where f of x has this particular structure. And what we want to do is just write down more examples of situations where, given the structure of f of x, we make a guess about what the solution will look like. I'm only really going to highlight 3 cases. One is the polynomial case that we just described. If f of x looks like a degree n polynomial, then guess that y will also be a degree n polynomial. Okay? Well, let me just stop here, okay? Because in the next video, I'll give you more examples like this, and we'll do some more examples. And there is a little wrinkle that is important to mention that we should talk about, okay? But this is going to give us a pretty nice entryway into the forced harmonic oscillator situation. Okay, bye.